Good day to everyone and welcome to new video lesson about zone software. Today I will speak about some theoretical aspects of inversion. And it's maybe too complicated, but it's very important problem. And it's maybe really interesting for all of people who doing conversion, especially non-linear inversion. So today I am going to speak about linearization because this is what all gradient inversion based on. So it's Taylor series used to one first member, first derivative and function is using in physical inversion because it's very time consuming, time and memory consuming to use first, second, and third derivative, for example. So it's limited to only first derivative. And it's very typical for most of physical problem to solve the inversion in this way. So the problem is used to in first iteration. Physics used to go through the pretty pseudo-linear problem where is non-linear property of problem is not so strong, and we can use just this linearization. But very important is first approximation. That means how close we start from the model we're going to resolve. So it's the found first initial approximation is very far from solution, it can be problem. I'm not speaking here about local or global minimum of inverse problem. I just would like to say that even they are looking for local minimum of solution. So for the good misfit, we need to have a good initial model, very close to this solution. But for linear problem, it's no problem. I mean, some potential field problem, it's ideal linear problems. Resistivity, DC resistivity is also very close to linear problem, so it's no problem, especially if we're doing ART inversion in mesh model, because we have we can start even very far from solution, and anyway we will have a good results. MT also is very good, but in case of two model, B model inversion, it can be problem. Also, what can be strongly non-linear in near surface geophysics? First of all, it's time domain electromagnetic method. And it's very important to find good start approximation. For example, we typically starting from half space. If this half space value very far from conductivity of solution, it can be some problem, and we can have a not satisfied solution. So we need to do something with it. First of all, we can try to start from different initial model. Yes, this is right. But another way is using of more deep linearization. What linearization is? Linearization is splitting of our function to Taylor series and using only two first members. As I already said, it's function and derivative of function. So it's maybe a problem if we faced with very non-linear problem. For example, early times for time domain electromagnetic can point it in first derivatives to the two different routes of solution. And it's a non-linear problem, and it's a very complicated for inversion for the black box to understand which side to choose, for first route or for the second route. So in this situation, there is no predication what result should be. This is deal with the problem of derivative in different, even very close point of model can have strong difference. And so we will have a sometimes very strong steps to model on the first iteration if starting model not so close to solution. But they can use uh, another way, choose another way, and this is a way of more deep linearization. So I suggested this algorithm based on three Jacobian solutions to overcome the problem of big steps of first iteration. It's somehow averaged these steps on the first selected number of iteration with more deep linearization. Here I have added special submenu about linearization where can be chosen linearization of on the first iteration. For example, here is selected for first three iteration and vicinity of solution, which mean that our derivatives will be blurring around vicinity of current model in the radius of, for example, here 0.5. What does it mean? It's mean that we will have not so big steps on the first iteration. It will be a kind of average. Why? Because we took three models from upper of current model, from down of current model and current model. And we use not Taylor series, but sum of these three time series from the three initial model. That give us more smooth and stable solution on this selected first three iteration. For example, if we choose very high resistivity, it's not so good for time domain electromagnetic initial model. We anyway can resolve for our model. For example, here I have some very non-linear example with three components and with very long intermediate zones. You can see from apparent resistivities, it's very far from real resistivity of model. That's mean this is complicated problem. And I choose not correctly will be start from 100 or 50 ohm meters, but here is 1000. But I can choose a big vicinity. For example, it's in units of model, so it's natural logarithm. So I will start from free solution. First of all, will be here. It will be not used that much because it's far from solution. It has a big misfit and another something here. So it will properly jumped to our model. Of course, it's not a global minimum of solution, it's some local minimum. Nobody saying about global minimum. It's just about overcoming problems of first big steps on gradient inversion. So I'll try to do inversion. Well, it fits pretty good. Of course, if we choose very big, if we choose very big vicinity of our linearization, so very deep linearization, it will not so good for misfits if we have a very successful start model. So this free iteration will be uh, uh, will have a convergence not so good like the standard linearization. But if we don't know about our initial model, we anyway will go to our solution. Let's check it here. For example, it's even more complicated case. And okay, after 5 iteration, everything went well, and we put our model to minimum of solution. I don't know it's global or local, but anyway. And it's I'll try, for example, now from another example from 5 meters. It's also not so good because it's very far from a real model, but I hope to take something. Okay, and it's again work. Of course, we can do again. Repeat our inversion, and now we have pretty good misfit, you can see. And we don't need to choose some initial model correctly. So sometimes it may work. Unfortunately, all such things take much more time. And for example, for 2D or 3D models, it will take 3 times more memory because they need to keep a free copy of Jacobian matrix and analyze it and do some stuff with that. So it's maybe good for 1D problem, maybe for 2D, but not sure. It's a game. And it's linearization doesn't apply to thicknesses because there need much more sub-steps for this algorithm. It's not so easy like for parameters, because if we change thicknesses, all thicknesses lower, this thickness will change. So we need to have much more Jacobians for analyzing to get this deep linearization for resistivity and thicknesses together. So now it's correctly worked here only for resistivity and another call parameters and not for thicknesses. So thank you very much, and I hope you find this video lesson interesting. Bye bye.